Today's topic is escape velocity of particle under central force. Okay, so we have to find the escape velocity of a particle in central orbit under central force. Okay, before going to discussing about it, we here give a rough definition or general definition of escape velocity. And escape velocity is defined as a body is projected from Earth with a certain velocity. Okay, that is, a body is projected from Earth with a certain velocity. This is initial velocity or velocity of projection, such that it will never come back to the Earth. Okay, so the value of the velocity is such that the body will never come back to the Earth. That is, the body is beyond the gravitational field of Earth. Okay, and this type of velocity or this initial velocity of projection is said to be escape velocity for that body. Okay, but here we discuss about the escape velocity of a particle under central force. So we first take a central orbit, let it be the central orbit, and let this is the initial line, this is the pole, this is the initial line. Okay, and let the particle on the central orbit, we write the central orbit like this. Okay, let the particle on central orbit at P, this is the position of the particle, and clearly this is the radius vector, this is r, and this is the vectorial angle, this is theta. Okay, and we draw a tangent at P which is given by PT, which meet or cut the initial line at P. And from differential calculus we know that the angle between the radius vector and the tangent at P is given by phi. Okay, this is taken to be phi in differential calculus. And since it is under central force, so must be central force act along the center of force. This is O, let it be capital F of R. This is the central force. Okay, and this is obviously tangential direction. This is the positive tangential direction, and we know that the tangential equation of motion of the particle is given by, this is v dv ds. This is tangential acceleration per unit mass, and on the right side we first find out the tangential velocity which act on the body at P. Since this is the central acceleration, this is always act along the radius vector in the direction of center of force. So the component of f of r along this side, because this is phi, so we write this is f of r, this is cos phi. Okay, and in differential calculus we know that we write this is f of r into dr ds, s with the arc length, and this is measured from a certain point, let it be the fixed point A, and here AP, this is S, this is the arc length. Okay, and this is in the opposite direction or positive direction of tangent. So we write this is equal to minus f of r into dr ds. Right, now if we cancel out dr from both sides, we get the equation as v dv. This is equal to minus f of r into dr. Now it is assumed that the particle start from a velocity or start from r equal to a with a initial velocity v equal to v0, and here it is clear that this is the point r theta. So here r equal to r and let v equal to v. Let the particle be at velocity v at the point p after time t. So we integrate both sides by the range. Here this is v0 to v and this is v dv, and if we multiply left side by 2, then we also multiply right side by 2, and integrating we get minus integration. This is r equal to a to r. This is f of r dr into 2r. Okay, so from left side we get by integrating v square, and this is given by v0 to v, and from the right side we get minus 2 into integration r equal to a to r. This is f of r dr. Putting the range of integration, we get the result as this is v square minus v0 square. This is equal to minus 2 into integration a to r f of r dr. Okay, now we write this relation as v square, this is equal to v0 square minus 2 into this integration can be taken as integration a to infinity f of r dr. We take the first integration from r equal to a to r equal to infinity f of r dr. So we must be subtracted from this integration by r to infinity f of r dr to get the above line. Okay, here we get a to infinity and subtract r to infinity. So we get the result integration a to r as in the previous line. Okay, and we write this is v0 square minus 2 into integration a to infinity f of r dr, and the last term is plus 2 into integration r to infinity f of r dr. Now the range of the second integration, this is from the initial value to infinity. Okay, and we put this value, that is we put here this is v square, this is equal to 2 into integration a to infinity, this is f of r dr. Okay, now putting this value we get this is v0 square minus v square plus 2 into integration r to infinity, this is f of r dr, and left side is obviously v square. Now if we taking limit as r tends to infinity, and from this relation we get this is v square, this is equal to v0 square minus capital V square, because if we taking limit r tends to infinity, then both the limit of this integration is infinity to infinity, and since both the limit are same, so the integral value must be 0. Okay, now if we take the value of v0 square less than value of v0 less than v, okay, then from the right side of this relation we get the negative result, that is v0 square minus v square less than 0. Okay, but the left side is a perfect square, so this is not real. Okay, so our initial velocity v0 must be greater than or equal to v to reach the particle to infinity, because we take here r tends to infinity. Okay, and this velocity, that is the velocity v, which is given from this relation. Okay, this is capital V square, this is equal to 2 into integration a to infinity, where r equal to a with the point of projection. Okay, and f of r is the central force. That is, if v0 greater than v or v0 equal to v, then we are able to project this particle to infinity in central orbit. Okay, so for this reason v0, this velocity or this value of velocity is said to be escape velocity of the particle in the central orbit. Right? So we have to find the escape velocity of a particle in a central orbit from this relation. Right? Now, in particular, if we take the central force which is inverse square law, that is f of r, this is equal to mu by r square. And we know that if the central force is inverse square law, then we get the central orbit is a conic section. Okay, and we already discussed in a class of central orbit, we discussed that if the force is like this, then the central orbit is conic, and conic may be ellipse, may be parabola, and may be hyperbola. Okay, and in this case, we get the velocity at first from here. This is given by v0 square equal to 2 into integration a to infinity. This is 2 mu by r square dr. We cancel this 2 because we let here 2. And by integrating, we get the result as this is mu by r. This is minus obviously. Okay, and sorry, this is 2 also. And now putting the range of integration, this is a to infinity, and getting the result, this is 2 mu by a. Okay, and in this case, the escape velocity for the orbit under inverse square law is given by v square. This is equal to 2 mu by a. And we know that for elliptic orbit, v square is given by mu into 2 by r minus 1 by a. And for parabolic orbit, we get this is v square equal to mu into 2 by r. And for hyperbolic orbit, we know that v square, this is equal to mu into 2 by r plus 1 by a. Okay, and here we let the initial point of projection, let r equal to a. If r equal to r we put, then we get for the parabolic orbit, this is given by parabolic orbit. Here we write parabolic orbit v square, this is equal to 2 mu by r. Okay, because we put r in place of a. And for hyperbolic orbit, v square, this is mu into 2 by r plus 1 by a. That is here we add some quantity, so we write here v square greater than 2 mu by r. Okay, but in the elliptic orbit, we say that v square less than 2 mu by r. Okay, so if the velocity is v square, this velocity is v square greater than or equal to 2 mu by r, then the particle in central orbit under inverse square law forms a parabolic orbit or a hyperbolic orbit. That is, the particle forms like that. This is the parabola, this is the parabolic orbit, or hyperbolic orbit means this is hyperbolic orbit. So if we project a particle in a parabolic orbit or a hyperbolic orbit, then particle can never return to the point of projection again. But in elliptic orbit, if we project this particle like that, then the particle must reach the point of projection after complete revolution. So in this case, this is not in escape velocity, but in this case, in this or this is in escape velocity. So we say that under inverse square law, the escape velocity is 2 mu by r, right? And this is the complete discussion of escape velocity of a particle under central orbit, right? Thank you for watching.